Hi everyone, this is my favorite topic in mechanics, energy. Now I'm not a physics person, I'm not into physics at all really, which is probably a silly thing to say because mechanics is very physicsy, but it just doesn't feel like it to me, it feels mathsy. So if you're like me and not very physicsy, then these definitions are going to be quite helpful, and it would take more of a physicsy person to tell you exactly what they mean. Okay, so we're talking about energy here, and our topic is Comep and Wep, and Comep stands for Conservation of Mechanical Energy Principle, so it means that energy is conserved, and the work energy principle means that that energy has been lost through work, and we'll explain what work is. But basically, when an external force has acted on a particle, energy will be lost as a result. Okay, so what is the formula for kinetic energy? Well, we know that's half mv squared. So we're just going to run through some definitions here. What is the formula for gravitational potential energy? Well, this is mgh. Think about why that is gravitational potential. If this is our kind of base level here, and we raise a particle up a height h, you know that the force, the gravitational force is mg. So basically, I guess the higher that this particle raises, the more potential energy it has, because it's going to fall, isn't it? And it's going to gain kinetic energy as it falls. It's going to increase its speed. And the bigger h is, the more speed it will have, obviously until it hits terminal velocity, but we're not really considering that right now. Okay, and how do they relate to each other? Well, let's consider a pendulum. Consider a pendulum at the 3 stages of its swing. So if the pendulum starts here at the top, okay, if there's mg again, here's height h, you can see that it's EP, so I'm going to call gravitational potential EP, and kinetic energy is EK. Okay, so EP must be its highest here, mustn't it? It must be mgh. But at the top of that swing, our kinetic energy must be 0. It's right at the apex, just before it starts to fall down again. And then what happens as it comes back round here, and let's say this is our base level then, can you see that mgh here would be 0? Our gravitational potential is going to be 0 because it's at its lowest point, h is 0, mg times 0 is 0. But it's swinging the fastest it can possibly be, isn't it? So that's our half mv squared, right? And then it's coming back up again to the apex of the swing, and again our gravitational potential is really high because it's the maximum h that we can have, and our kinetic energy is 0. So can you see this transfer of energy, the conservation of energy, because energy is just moving between kinetic energy and gravitational potential energy. Okay, now this links into work. So what is the definition for work? Well, work done is defined by force times by the displacement moved by that force, so the distance moved by that force. Okay, think about what that means. If a force is pushing on a particle, let's say here F, and it has moved it 10 meters, then you would say the work done by that force, okay, is F times S. So let's say the force was 20 newtons and the distance was 10. The work done is 200 joules again. So joules is our unit for energy, and work is considered, and work is, well, I don't want to go into it yet, but work is the loss of energy. Okay. So through an external force. So when work done is positive, that means that the particle has been moved in the positive direction, i.e. the direction of the force. Okay. If a particle, let's say friction then, particles always move in the opposite direction to friction, don't they? That's what friction is. Friction always opposes movement. So if we said work done by friction, so let's say this thing moved 20 meters down this slope, friction's acting to the right, isn't it? So this would be negative work done because the particle is moving down the slope, but friction is acting up. Okay, so we would consider that negative work done. The particle is not moving in the line of direction of the force. That is what work means. Positive work means particle is moving in line of the direction of the force. Okay, and that's where energy is lost. Negative means it's moving in the opposite direction to the arrow of the force. Okay, and you're going to see how we can build up this formula for Comep and Wep, and you'll see for Comep, where no external forces are involved, it's just gravity, and you'll see it's the interchange of kinetic energy and gravitational potential. Okay, so best way I think to generate this formula, which always works, and again, every teacher thinks they've got the best way, and I really think this is a great way to do any of these Comep and Wep problems. Okay, so first we're going to do Comep. Imagine we've got this smooth slope here then, so no external frictions is involved. I've got this mg here, right? There's my particle, yeah? And let's say we're going down the slope. So let's say it starts here with speed u, it finishes here with speed v, and it's moved s meters in the direction downwards. Now, this is a SUVAP problem, isn't it? Okay, it's got s, it's got v, it's got u, it is accelerating from u to v. So we know that v equals, we know that v squared, sorry, is u squared plus 2as. This is a great place to start. Because can you see, if I times everything by a half m, a half m, a half m, get that 2 in there, just rub that out. So half m 2as. Okay, can you see straight away how we've got the link between kinetic energy and gravitational? This is initial, sorry, not initial, this is final VK, isn't it? Because it's got final EK, because it's got a V in there. Can you see this is final EK? That is kinetic energy for the final velocity. And then we've got our initial EK, because our velocity is u this time. Okay, so at the moment we've got final EK equals initial EK. And then here, what's this bit about? Well, we need to, you know, tighten this up a bit. So this is MAS, because the half and the 2 cancel. But what is MA? Well, we know that when acceleration is constant, F equals MA, doesn't it? F equals MA. And notice this whole thing is based on constant acceleration, everything I'm doing here. If we weren't using constant acceleration, we would have to use integration and differentiation to do this. But in this syllabus, this is how we're absolutely fine to do what we're doing now. So what is this MA? Well, we know F equals MA. So this is FS. Wow. It's all coming out now, isn't it? This is the work done formula, isn't it? But what do we mean by F? F is the resultant force. Really important you understand that. So this is the resultant force, which means, and that's what this F is. The resultant force is mass times acceleration. So on my diagram, I need to start putting in some forces. So if this is theta, this will be theta. So this is mg cos theta, and this would be mg sine theta, right? Also, my diagram's looking a little bit clouded. So let's do this actually. So force, this F part, the only force involved is going in the direction of acceleration, isn't it? So this is positive mg sine theta, and then we've got S. Now, mg sine theta S. Well, that doesn't quite look like gravitational potential energy, but it will do. Think about what S sine theta is. If I put this S here, big triangle here, sorry, I know it's looking really quite messy, but hopefully you can follow this. This angle here is theta, okay, and this is our height, h. Remember, gravitational potential works on height. So can you see from that triangle I've drawn, sine theta is height over displacement. So if I times up by s, actually, extend that, actually s sine theta is h. So s sine theta is h, mgh. Ta-da! This is gravitational potential energy, right? So we're saying final EK equals initial EK plus our gravitational potential energy. So plus our MGH, right? But it could be minus, couldn't it? It could be plus or minus MGH, right? Because what happens if the thing was traveling up the slope? Okay, if it was traveling up the slope and U was going up and V was going up, our mg sine theta, our component, mg sine theta, this would be negative, wouldn't it? It would be in the opposite direction. And this is where we need to make a really clear point, that mgh, our gravitational potential energy, is actually the same as work done by gravity. Work done by gravity. Think about why that is. That is force times distance, isn't it? Work done is force times distance. mg is the force, h is the distance. So think about it. If the thing is going down, i.e. h is going downwards, that is in the direction of gravity. So that's always going to be plus. If the thing's going up, it's always going to be negative because gravity works down. If your particle moves in the opposite direction to motion that the force is intending, then it's going to be a negative work done. So this is why I say for the final formula, so final EK is initial EK plus or minus work done by gravity. Okay, so this is Comep, right? Comep, really important. But now we can step this up and we can generate Wep. So I'm going to generate Wep now. All right, so now we've got a rough slope. So that means that we have an external force involved. This time, let's make the particle go up then. Maybe that will make things a bit, mix it up a bit. So theta's there. Okay, so we've got our normal reaction. We've got our friction this time. We've got our mg sine theta, and we've got our mg cos theta. It has moved s, and it ends up here. Okay, so same starting point. So v squared, u squared plus 2as times by the half m. This is how we make the formula, okay? But you don't need to do this every time. So there's our half mv squared, half mu squared. The half and the 2 cancel, and we're left with MAS. We know that MA is our force, and F equals MA, and MA is our resultant force. So let's think about the resultant force. How do we find the resultant force? F equals MA. We know that we need to do things in line with the way things are traveling, right? I've put accelerating going that way, but actually we know it's going to decelerate, don't we? We know it's going to decelerate, but all of my v and u from my suvat is in the relative direction going up. So I'm going to keep things going up. So I'm going to resolve. Okay, so force going up the slope, nothing. But force going down is minus friction and minus mg sine theta equals mass times acceleration. So now I put that in here. So minus mu r minus mg sine theta. Times that out, and I get half mv squared, half mu squared. minus mu rs minus mg sine theta s. But we know sine theta s is h. So this is half mv squared, half mu squared, minus mgh, minus mu rs, right? So we're there, because think about it. This is our final EK. This next one is our initial EK. The next bit is our plus or minus work done against gravity. Remember, h has moved up, and gravity always acts down. So the particle is going up, but gravity goes down, so of course it's going to be negative in this instance, which it is. And then we've got our work done by friction, because we've got our force, mu r, times by distance, s. So I'm going to call this WE, where WE is work done by external forces, okay? So sometimes they're going to be in favor, so plus, i.e. the particle is going to move in the direction of the particle. Sometimes it's going to move against it. So this is called Wep, and remember Comep just doesn't have this WE section. Right, let's see how we use this in practice. So one example here, and then the next video we get some more examples. So a particle of mass 3 kilograms is projected with a speed 10 meters per second up a slope, and it's rough. So let's just quickly draw that. So rough, does it tell us? Yeah, 30 degrees. We've got, it's projected up, so U, and it's going to end up somewhere with V, right? So it starts at 10 meters per second. Coefficient of friction is 0.4, so that's 0.4 R. There's R. Start using some different colors. Do we know its mass? Where's the mass? 3. So 3G. Force going down. So this is 3G sine 30. And this is 3G cos 30. Great. And V, do we know what V is? The coefficient of friction is 0.4. Calculate the distance of travel before coming to rest. Okay, so that means V must be 0. As soon as it says rest, we need to calculate that S, or I'm going to call it X, because sometimes S looks like a 5 in practical work, doesn't it? So I'm just going to call that X. So it wants us to find X. Okay. Is this a Wep situation or a Comep? Yes, correct. You're thinking Wep because it has an external force. It has friction, right? So I quote Wep. This is how I practically use this. I'm going to quote Wep, which is final EK equals initial EK plus or minus work done against gravity plus or minus work done against external forces. Let's go. Okay, so direction it's traveling is up. So half mass, which is just 3, not 3G, times V squared, right? And V is 0, because it's the final EK. Half mass 3, U squared, 10 squared. Plus or minus work done against gravity. Is it going to be plus, or is it going to be minus? It's going to be, ta-da, minus, because it's moving up the slope. So minus work done against gravity, which we know is mg times by h. And then we've got our work done against external forces. Is that going to be negative or positive? Ta-da! It's going to go negative, because the particle's moving that way, but gravity moves. Friction is acting against that thing. So minus force, which is 0.4 R, times by distance, which we know is x. That's the distance this thing has traveled, okay? So there's a couple of things we need to find. This is 0. 10 squared. So let's work this stuff out. So 10 squared divided by 2 times by 3 is 150. And then we've got this 3GH. I'm trying to find the distance the particle travels. So that's x, isn't it? I need to find x, but I've got an expression for h at the moment. Okay, not a problem though, because just like in the proof of where this thing came from, I just need an expression for h. I've drawn a little triangle here. I can see that sine theta must be h over x. Can you see? So x must be h over sine theta. So, and theta is 30 degrees. So x must be, h must be, I'm not trying to find x. Here we go. Right. H must be x sine 30. Okay? I hope that made sense. Minus 0.4 and then r. What's r? Well, I know that's 3g cos 30. Don't know. We're back to our simple resolving format. So now I just need to rearrange to find x. So again, I'm just going to do this quickly because I know, well, hopefully you're pausing the video and you're thinking, yeah, I'll just do that, calculate that. So 3 times that, plus 0.4 times that, times cos 30. So I get 6.03 to 3SF. Remember, that's the maximum you can give. Brilliant. So part B. Calculate the work done against friction. That's easy, isn't it? That's your WE section here. What is work done against by friction, WE or WF, whatever you want to call it? That is force times distance. So we already worked out the first bit. Okay, so the force was 0.4 R, 3G cos 30, and our X we just worked out was 6.03, but remember you're going to use the exact answer, 27 blah blah blah. So times 0.4 times 3 times 9.8 times cos 30. So that's 61.4 joules, okay? Now, you might be thinking, well, it's negative because it's going the opposite direction. The actual absolute value of work done is 61.4, but it's in the negative direction. Okay, so for our calculations, we're saying it's negative because it's all relative to this upward motion, but the actual magnitude of the work done is still 61.4 regardless of the direction. Okay, so the next video is going to have much more examples than that. We've proved, we derived it from scratch, and now you've seen it actually work in principle. Let's do some more.